Okay, sorry for the disturbances. So I'm going to talk about the project I have been working on. It is called skin lesion detection in dermatological images using deep learning. I have been working on in this project for the past year, I believe. And this is joint work with Dr. Jimena Alvarez and Dr. Boris Escalante. Well, this is the outline of the talk. I'm going to start with the medical context which we're trying to address. After that, I'm going to give you a little bit of the introduction of the evolution of computer vision systems using deep learning. And after that, I'm going to tell you about the model that we chose to use, as well as the datasets that are key to make this work. And finally, I'm going to show you some results and a little demo of what we have accomplished. So the motivation is that in the US, for example, we have more than 5 million new cases of skin cancer each year. From this, melanoma is a rare type of skin cancer. However, this kind of malignancy is the most lethal. As always with cancer, time is key. So the survival rate is 99% for a patient who has been diagnosed in the early stages, and 14% for a person who has been diagnosed in the later stages. So what about Mexico? Well, in Mexico, the melanoma is responsible for 80% of deaths from skin cancer, and it is increasing all around the world. And according to the National Institute of Cancerology, it has increased from 300 to 500% in recent years. So the AI community began to pay attention to this problem after the publication of this article. This is work from Andres Esteban, Brett Cuprell, and Sebastian Tron from Stanford University. And they show that if you train a deep learning model, they chose to use Inception V3, and they gather the biggest amount of data available at the moment, and they compare the performance against 21 board-certified dermatologists. Their system was able to classify over 700 different skin lesions, but they were particularly interested in these two cases: carcinomas versus seborrheic keratosis, and melanomas versus naked. We need to say that these are pretty similar images, so are the critical cases for medical specialists. So that's why they were interested in this. So the results show that the convolutional neural network was able to achieve a better performance than medical specialists, and they proposed to optimize the system to be embedded in a mobile device so that this kind of technology can reach places where there is difficult to find a dermatologist. So the first kind of applications of CNNs were only used for classification. That is, I give you an image and you give me the label of what is in the picture. And the natural step was detection. So why not locate all the objects of interest and classify them? So why do we need to design a real-time object detection system? Well, they are working right now in autonomous vehicles. They have been used for face recognition, surveillance systems, and obviously for medical purposes, for example, detection of breast cancer in ultrasound images. And I'm going to show you just another application. So the model that we chose to use is trained on this dataset, COCO. It is a massive dataset with this kind of characteristic, over 330,000 images, 80 categories of objects, and object segmentation. You can see here some samples of the kind of images you can expect in that dataset. And obviously, it uses ImageNet. And ImageNet, of course, as you know, contains over more than 4 million images belonging to 20,000 different classes. So the model that we chose to use is YOLO-V3. It's a state-of-the-art detection system. It uses a special method that allows it to be trained with COCO and ImageNet. It is able to perform multi-scale detection. And if you input an image with a resolution of 320 by 320, it is able to give you a result in just 22 milliseconds. So YOLO has a similar performance to other kind of state-of-the-art models, but it is a lot faster. And it is built upon this neural network. It's called DarkNet by Joseph Redmond. And DarkNet has 53 convolutional layers, and it is mainly based on 3x3 filters, followed by 1x1 filters. This is a summary of the network, and as I told you, it's mainly based on 3x3 and 1x1 filters. So this is the base to build YOLO, and YOLO is composed of 106 convolutional layers. The difference is that it tries to apply the concept from ResNet. You can see the skip connections here. And it also uses detection layers as well as upsampling layers. So with this kind of tricks, the strongest features reach the deepest part of the network. And during the training process, it tries to solve the vanishing gradient process, the vanishing gradient problem. So this way, the first filters are able to be updated. So the algorithm starts with k-means, and it tries to look for previous regions in which the object might be found. And the output of YOLO is a vector of this nature, where P is the probability that there is an object in the scene, Cx and Cy are the coordinates of the center of the object, H and W is the bounding box, height and width, and C1 to Cn is the probability that the object belongs to one of the classes. So for the V3 version, things haven't changed much. This is just a tensor that is repeated 3 times because we perform multi-scale analysis at 3 different scales. So the prediction is performed via the bounding box parameters, and it gives you a probability. After that, it applies a threshold so that we only keep the high scores. So this is a summary of what I have told you. This is an image. It tries to look for previous regions. After that, after the inference process, the network gives you a lot of bounding boxes with different probabilities. You threshold those values, and then you keep only the high scores. It uses a multi-label classification approach, so that means that an object can be of another class. It can happen. It uses independent logistic regressions. It allows better inference times. And of course, during the training stage, it uses 2 different loss functions, one for prediction and one for classification. And it tries to optimize both. So this might be of good use to dermatology because they perform visual examination to diagnose a skin lesion. So I'm working with this dataset. It is composed of over 23,000 dermatological images. And as you can see in the first row, these are benign lesions. In the lower row, you can see malignant lesions, and they are pretty similar. So this is a very challenging task for computer vision algorithms, as well as medical experts, of course. So we had the following hypothesis. Is it possible to use YOLO that was designed for a completely different task to a medical application? And we found that it is possible using the well-known strategies as transfer learning and fine-tuning over all the convolutional layers. So we also use data augmentation. Some of the transformation that we use are horizontal flips, random rotation, and transformation in the colors in the hue and saturation components. Because as you know, well, deep learning models tend to learn the most, and if you give them a lot more data. So in the dataset that I told you about, we decided to partition it 90% for training and 10% for validation. And these are some of the results. And you can see that, for the 150,000 iteration, we get satisfactory results. The metric that we're using is precision, and the other one is recall. So at the end of the training process, we got 74% for precision, 74% for recall using data augmentation. And these are quite nice results, however, they can be improved. These are some visual results. We need to say that these images haven't been seen by the network. They were given to me by a dermatologist. The white letter shows the ground truth label, and this is the prediction that YOLO gives. You can see the tag and the probability of the object that you are seeing. We are trying to classify 3 different skin lesions: melanoma, neri, and seborrheic keratosis. So what can we do to improve these results? Well, we decided to use image processing as segmentation, and these are some results. We transfer the image to another space color, and you can see that it has a greenish yellowish tone, which we can use to extract the lesion using algorithms like GraphCode, and these are some examples. However, not all the results are this pretty, so we decided to use another segmentation technique, which is based on edge detection. And these are some results. We have the image, we transform it to grayscale, we apply a Gaussian filter, and then the canny edge detection filter, and we get this kind of results. Then we apply morphological operations to dilate the edges, and we ask the program to find the biggest contour and fill the area inside of it, and we get this kind of results. The segmentation is not perfect, however, it doesn't matter for the model because the dermatologist uses the surrounding skin to deliver you a diagnosis. So I'm going to show you very quickly a general demo and then a medical demo about what YOLO can do. So this is YOLO in real time, and as you can see, it is able to detect persons as well as objects. So we managed to retrain this model using data augmentation and segmentations to get some other results that I'm going to show you. So this is the same results that I showed you later, just running in real time. This is the bounding box with the probability of the object that the model is seeing, as well as the tag. Our future work is trying to optimize this model and deploy it on a mobile device so that we can achieve similar goals to the one that Sebastian Tron and Andres Debak proposed. I believe that's everything I have to say.
for your training, you said you basically decolorized it, or you exploited that the color is not important because you changed the hue and saturation and all of this.
Yes.
It looks, I'm not an expert on this, but it looks like color might actually be relevant in this case.
No, color is really relevant, but it somehow keeps the properties independently if you use it in BGR space color or HSB space color. The dermatologists, they use a special rule that is called ABCDE. A is asymmetry, B is border, C is color, D is diameter, and E is solution. So this way, a patient goes to the dermatologist, and using these rules, he delivers at the diagnosis. So the same descriptors, because we are using color images, are being extracted in the convolutional layers in yellow.
But so the color is not being, because I thought that you were manipulating the color and retraining with it.
Yes.
So does this have any impact? Because I could imagine it might decrease the performance from the perspective of you might be reducing the knowledge from color, but it could increase the performance in terms of all the other ones because they're saying it's unchanged for them.
I am using the color and it is being changed for all the dataset. The transformation is only used for the segmentation process, but I turn it back to BGR color.
Okay, that makes sense. I missed that. Thank you.
So I see that you have trouble with the small data set. So this is why you're trying all these augmentation techniques, etc. But when I look at the output of your network, you're actually, I mean, what drove the choice to use the full network, including the bounding boxes and the potential for multiple objects in the image when you want to see if one individual image is classified as either winner or not?
Yes, in this first version, I'm just not exploiting the full capabilities of the model because there are so many images to relabel them manually. So what I did was a strategy to only center the detections at the center of the image. So it learns that it learned that the lesion is only located at the center. That's why you are only seeing one detection. However, if I segment all the images and I paste them, it will obviously learn that it can be in different regions and the capabilities will be exploited, but I didn't follow that road.
What I meant is the exact opposite. What I meant is you probably don't even need the capability of having multiple objects in the image that are not in the center, because if you want to check if this is actually a melanoma, you check it, you put it in the center of the image, and then you can check it right away. So I think many of the parameters in the model that you're trying to train with the small data set, that you need to train because they are in the model, are actually just dedicated to doing these things that you can have multiple objects, that they are different positions, etc., etc. That you can basically just get rid of, have less parameters, and
just
have better classification performance with the small data set. Because I think you're trying to train, you're trying to make the model learn things that you actually don't need.
Well,
at least from my perspective.
Well, dermatologists have an interest also to detect multiple lesions. There are some kind of scanners, so this kind of techniques might be of good use. We received sometime the visit of a medical doctor, and he told us that there is some kind of scanner that scans, that outputs some region of your skin, and is able to detect the different lesions that might be in that region. It can also be used for some kind of face scanners that can detect the multiple lesions that might be present in your face. So that why we decided to explore that road.
Steve, thanks.